Happy Friday to everybody out there. Yeah, if you haven't brought your homework up yet, please do so. I don't think I have any announcements. Do you guys have any questions or comments? You doing okay today? I did want to make, actually I do have one quick announcement. Homework 2 is not due for, I don't know, like a week and a half or something like that. So I'm hoping that none of you have started on that too much. I am going to make a slight change to that assignment, and I will post that on Carmen over the weekend here. So nothing too crazy, nothing too much change. I'm just going to shuffle some problems around. So if you haven't started on that yet, good. And if you have, I hope you haven't done too many of the problems yet. Have you guys already started? No? Okay. Yes. I won't make too many changes. I'm going to make I'm going to remove a problem or so from that list and maybe add one other one in. Anyway. Well, if there's no further questions, we can go ahead and get started with our lecture today. We're going to resume our discussion with Chapter 3 today, looking at discrete random variables. So last time we introduced this idea of a random variable, and our formal definition here is that it's a function from our sample space into the real numbers. So again, our sample space can look like anything. So far we've talked about flipping a coin, dealing cards, getting a certain hand of poker. It can also be something that's a little more numerical, like the lifetime of an electric light bulb, something like that. So our sample space can be anything, but a real number is a random variable is going to be how we map that into some sort of a number we can work with a little more easily. And just our notation, remember, uppercase letter is going to represent a random variable, and then a lowercase letter is going to represent a particular value of that random variable. So last time we looked at a few quick examples of that. We looked at the coin flipping example, the concrete beam, how it fails, and we also looked at the lifetime of a light bulb. And this leads us to this sort of a separation in types of random variables. So our random variable here, we can have it be one of two types, either discrete or continuous. So here I'm at the top of page 2 of your chapter 3 notes. So yes, we have two types, discrete or continuous. Our first type, discrete here, discrete random variable is a random variable whose possible values either constitute a finite set or can be listed in an infinite sequence in which you can order them. So it's a finite set, you can actually write them down. Or it could possibly be some infinite list, but it's going to have some ordering. For those of you who have taken some more advanced math, you know that's called countably infinite. So it can be the list can be infinite, but it needs to be countable. That's going to be our discrete random variable. And of those three that we looked at already, this would be examples 1 and 2. So this was our coin flip. Coin flip example. In that one, we saw that x could be, for example, 0, 1, or 2, or just a 0 or 1. That was that option. And then the concrete beam. Again, x was 0. Sorry, x was 1, 2, or 3 there. 0, 1, 2, or 3. So in those two previous examples, again, those are discrete random variables just because we have sort of a finite set of possible outcomes. We can write them all down. Those are our discrete random variables. So the other type of random variable, which is something we'll talk more about in Chapter 4. Chapter 3, obviously, we're talking about discrete random variables. But this other kind of continuous random variable is such if both of the following are true. If the set of possible values you can get either consist of a single interval or some union of disjoint intervals. So something like 0 to 10, 20 to 30, maybe the union of those two things. So if we need the possible values to take on some sort of an interval, and also that the probability of any particular value is 0 for any value c that's possible there. And so this would be example 3 with the lifetime of a bulb. We saw that x needs to be in 0 to infinity. So the range of values I have there is some interval 0 to infinity, and therefore it's a continuous random variable. And we'll talk more about these later, but just kind of show you this is the other type. And then continuous random variables often correspond to some data that you measure. So if I was interested in looking at the height of people or some more scientific measurement, that would probably be a continuous random variable. Okay, so those are our two types of random variables. Again, we're going to talk mostly about discrete random variables in this chapter. We'll come back to the continuous variety later. Maybe I'll just make a quick note that it is possible to have a random variable that's both types, so that's somehow mixed between these two things. That's both discrete and continuous. We won't talk about that at all, but just to make a note there that it is possible to have both types in there. Okay, so let's do a few more examples here. Another sort of very simple example. This looks like something we've already done before, but wanted to do it one more time. So again, let's say we're going back to our favorite coin tossing example. Let's say we just flip a coin. So we're going to let our random variable be a 1 if we get a head, and 0 if we get a tail. So let's write all this out very formally. So what's my sample space here for just a single coin flip? Yeah, I can get heads or tails, right? So my sample space, I can get a head or a tail. And then again, just to kind of formalize, to go from something that's sort of abstract, our sample space getting a head or a tail, we want to talk about this in terms of a number. So instead of saying we got a head or a tail, we're going to say that our random variable is either a 0 or a 1. And again, this is something we've defined. It could be the other way around if we wanted to. 1 if we got a tail, 0 if we got a head. But again, we're going to assign it this way. So the x of s, we have a 1 if we get a head, if the outcome in our sample space that we got is a head, and again 0 if s is a tail, if our outcome from the sample space is a tail. So again, just going from an abstract sample space to some numerical representation of that sample space based on the outcomes that we could get. And let me also just note here that the reason I'm showing you this example one more time is that this is a very special type of random variable, which we'll see later. So a random variable like this one that only takes on 0 or 1 has a special name. So random variable whose only possible values is called. Does anybody know what this is called? Binary. Okay, that's one way of, yeah, binary random variable could be 0, 1. We're going to call this a Bernoulli random variable. Bernoulli random variable. So exactly the same idea as a binary random variable. The terminology in statistics is Bernoulli there. Okay, and we'll see. This guy will be popping up again later. We'll see him more. All right, so before we move on to section 3.2 in your notes, I wanted to do one more example. Again, I apologize. I feel like I sort of flew through the first chapter of notes, and I want to kind of throw more examples in here as we move forward. So this is actually out of your textbook, but one more example here. It's not written in your notes anyway. If we let our sample space equal the set of all 5-digit zip codes, and we define a random variable x to be the number of non-zero digits in some randomly selected zip code. So again, our sample space is going to have a lot of different things in it. 9. I'm not going to list all those out, but it's just again, a zip code is just a 5-digit number that has no restrictions on what it is. So our sample space, again, something kind of abstract, just 5-digit codes there. But we're going to translate that using a random variable into a number by saying that x is going to be the number of non-zero digits in just some randomly selected zip code. So what possible values of my random variable could I get here? If I'm looking at the number of non-zero digits, what are my possible values of my random variable here? I think I heard it. 1 through 9? So I want to look at the number of digits out of 5 that are not equal to 0. Yeah, so I could have 0 up through 5, right? Those 2 that I listed there don't have any zeros in there, so they would be 0. I could also have all 5 of those numbers be 0. I don't know if that's a valid zip code, but for the purpose of this example, we'll pretend that it is. So x could equal 0, 1, 2, 3, 4, or 5. All right, so 3 people want to yell out what their zip code is. Do some possible outcomes here. Nobody wants to give away where they're from. 44646. Somebody else? 44236. And maybe 98607. 2541. What was the last number? 1. Okay. That's again just 3 possible outcomes. So again, remember, we're just randomly selecting a zip code, and we want to see how many non-zero elements are in that zip code. So here's 4 possible outcomes that we could get. Let's figure out what their x value is. So the random variable for 44646. How many non-zero elements do I have there? I think I said that wrong the first time. So if we're looking at non-zero elements, there's all 5 of those things are not 0. Similarly, the second one that was said has no non-zero, 5 non-zero elements there. 98607. Now we just have 4 of them that are not 0. And the last one also has 5 non-zero elements. So again, maybe sort of a trivial example, but here's a way that we could set up a random variable here. And again, this random variable, so we have a certain sample space, the set of all 5-digit zip codes, and I've picked a random variable. That's not the only one I could have picked. Can anybody make up another random variable that we could use here? Given this sample space? Even number, yeah, exactly right. So you would have to assign all the even numbers some number, right? So you could do like a 1 or a 0 if it's even, or say that again.
The number of even numbers.
Oh, okay, yeah. So we could look at the number of even numbers in a zip code. That would work just fine.
The sum of the 5 digits.
The sum of the 5 digits, that would be great as well. So some other examples here. We could also say y is the number of even digits. Maybe we could set z equal to the sum. So there's lots of other possibilities.
As a side note, I don't think it's possible. The way the zip codes are structured, you can't have one with fewer than 2 non-zero values.
Okay. Yeah. So maybe I'm violating some zip code rules here that you can't have all zeros. So that's maybe I shouldn't have a 0 or a 1 here, huh? Yeah. So if we want to be picky about our zip codes, if we want to be correct here. Any other questions, comments on this example? So random variable, again, it can be whatever you want it to be. Each application that we use will probably have sort of a natural one to use, but the point is that you could have more than one thing here. Okay, so that's the idea of random variables. And again, here in chapter 3, we're going to be talking about discrete random variables. So the important thing to talk about here, the main thing to talk about here is this idea of a probability distribution of a discrete random variable. So what that tells us is it tells us how the total probability of 1 is distributed among the possible values of x. So just as a kind of a bridge here between chapter 2 and chapter 3, in chapter 2 we assigned probability, or we calculated probabilities. We talked about finding probabilities to the various outcomes in our sample space. So we talked about what was the probability of getting 2 heads, or talked about the probability of having a certain number of concrete beams fail by one way or another. So we kind of talked about probability directly in terms of the sample space. So we looked at the probability of getting certain events from the sample space. Now in chapter 3 we're going to assign to the values of x. So instead of talking about probabilities for certain events in our sample space, we're going to assign probabilities to values of x. So it's kind of doing the same thing, but just kind of slightly changing our terminology. So let's maybe jump back to this example real quick. In chapter 2, we would have said that the probability of getting a head is maybe 1/2 if we have a fair coin. Probability of getting a tail is 1/2. Where in chapter 3, we would say the probability that x equals 1 is 1/2, or something like that. So instead of saying the probability of getting a head is 1/2, we're going to talk about some probability with and how that relates to the value of our random variable that we're looking at. So that's the slight difference that we're moving into now. Just that's a little easier to work with numbers instead of all the possible events that we might get. So that's the big idea of section 3.2. And so for discrete random variables, there are sort of 2 equivalent ways that we can specify these probabilities for x, or the probability distribution of x. The first one that we'll talk about is the probability mass function. We're going to abbreviate that PMF. And we can also define this using the cumulative distribution function, or the CDF of x. So what are these 2 things? Well, let's find out. So the probability mass function for a discrete random variable is defined for every number x as it's listed here. So we're going to use this lowercase p of x, p of lowercase x, and all that tells us what that means is that we have the probability that our random variable capital X is equal to some possible value lowercase x. And that's going to give us the probability of all outcomes in our sample space. So all so we want the probability of getting any outcome in our sample space that will give me that value of my random variable. So again, kind of here's that joint way of talking about assigning probabilities through events or assigning probabilities through the random variable that we're looking at. And there's two conditions that we need to hold here. The first one is that we need the probability of x to be between 0 and 1 inclusive. So it could be 0, it could also be 1 for all x. So for all x, so for any real number, we need that probability, this function little p of x, to be between 0 and 1 inclusive. So is everyone okay? This is real numbers. Everybody okay with real numbers? So that's our first thing. The second thing we need is we need that the sum of all x we need the sum of all those probabilities to equal 1, right? So remember talked about before, the total probability of has to add up to 1, right? You can't have a probability of bigger than 1. So if we add up all these lowercase p of x's, we should get 1. So that should make sense based on our previous discussion of probability. Okay, so this is what we're calling our probability mass function, our PMF. Let's take a look at an example here. So we want to consider a group of 5 potential blood donors. A, B, C, D, and E. We'll label them. Just have 5 people, each labeled with a letter. Of only our first 2, A and B have O positive blood. So, and we have a blood sample from each of these people, and we're just going to list these blood samples in a random order. So we're going to list them in a random order until we get an O positive individual identified. And we're going to let Y equal the number of typings or the number of things in the number of randomly selected people until we get somebody who has an O positive blood. So to kind of connect this to what we've done before, let's talk about what our sample space is. So I'm just looking at ordered out lists of these 5 people. So that's the sample space is going to be all permutations of the set A, B, C, D, and E. And maybe just jump back to chapter 2. How many elements are going to be in my sample space? 5 factorial, right? So I have this would be, I have 5 items and I want to choose 5 of them, which is just 5 factorial. So there are, which is 120. So I have 120 outcomes in my sample space there. Just all ordered lists of A, B, C, D, and E. And again, order does matter here. We're looking at these things in succession. Okay, so if Y equals the number of letters I need to look at before I get somebody who has O positive blood, what are the possible values of Y? So the possible values. What are my possible values for Y?
1 to 5.
1 to 5? So I could definitely, the first person could be O positive, of course. The second one could. The third one could. The fourth one could. But again, I have two people that have O positive blood. So when I get to the fourth one, if the fourth person is my first one that has O positive blood, then I can only have 4. So possible values are 1, 2, 3, and 4. Okay, so then what are we doing here? We want to find the probability mass function of y. So again, y can take on 4 values, so we need to find 4 probabilities here, and then we need to make sure they add up to 1. So let's get started here. Let's first find the probability of 1, p of 1, which is just the probability that y equals 1. So apologize, it's a little hard to distinguish a lowercase p from a capital P when writing it down. I'll try to make it very obvious. Okay, so now we need to think about how can the first, this is good practice for what we learned in chapter 2. Think about how it could be that the first thing that we get is, the first person that we get has O positive blood. So this is probability of y equals 1 is just the probability that that we type that A or B is typed first. So if either A or B comes first in my list of 5 things here, then my random variable y is going to equal 1. So is that okay? Why y equals 1 corresponds to A or B being typed first? Okay, so then what's the probability that I choose A or B out of those 5 letters? 2/5. Exactly right. So if you can make that jump immediately, that's fine. We could also sort of calculate this as usual. If we want the probability of something, we need to count the number of ways that can happen and divide by the total number of ways that total number of things in our sample space. So we have 5 factorial outcomes in our sample space, right? And if I want the first letter to be either A or B, then I have 2 choices for my first letter in that sequence. So I want that first letter to be A or B, and then the next 4, I don't care what order they're in, they will all give me a value of 1 there. So if I have 4 items left and I'm looking at all the possible orderings of those, that's going to be 4 factorial. So 2 choose 1 times 4 factorial is the number of ways such that we could get A or B typed first. The number of outcomes in our sample space that have A or B listed first. And if you work that out, you'll see that is indeed 2/5. So I know we rushed through, and I apologize again, we rushed through counting problems the first time, so I want to make sure that we're all on the same page here. Is everyone okay with what I wrote down there? How we can kind of figure out how many ways that can happen? Yes, sir.
Is it fine just to do probability of A plus probability of B?
Probability of A plus the probability of B. Oh, as in probability of getting A first or the probability of getting B first? Yeah, that works too, because think about they can't both happen first, so they're disjoint. So the probability of A or B being typed first is just probability of A typed first plus the probability of B typed first. Yeah. So each one of those would be 1/5, and that gives you 2/5. Good question. So yeah, and there's a number of ways to figure out what this probability is. I don't care how you do it, whichever way seems to work best for you. Okay, so that's our first number that we need to find. Little p of 2, that's the probability that y equals 2. So again, we need to think about what needs to happen such that such that y equals 2. So how can I get y equal to 2? What needs to happen for the first letter in my sequence?
It needs to be C, D, or E.
Exactly right. So I need C, D, or E typed first. And then I need A or B typed second. All right, so I need to get one of the other people first, and then I need to get A or B typed in that second position. So again, number of ways to figure this out, but kind of bridging back to our rules of probability, I'll rewrite this as, note that we have probability of something and something else. So we have a general rule for how to write out what that is. This is the probability that C, D, or E is first, times the probability that A or B is second, given that C, D, or E came first. So I'm just taking, again, this is the probability of A and B equals the probability of A times the probability of B given A. Just using that multiplication rule that we saw before. Okay, so what's the probability that C, D, or E come first? 3/5. And what's the probability that I have an A or a B in the second place, given that my first one was C, D, or E? 2/4, right? So if whatever I have in that first position, I have four characters, 4 people left to choose from, and I want all the cases that second person I choose of those 4 is A or B. So that's two out of those 4 people that I care about. So that's one way to solve this thing. Another way, kind of using more of a counting argument, which we can kind of jump to straight from that first line. So if I want C, D, or E typed first, and then I want A or B, that means my first. So this is going to be a fraction. We have 5 factorial total things here. For my first slot, I have 3 choices. So I have 3 choose 1 that I want for my first position there. For my second position, I need it to be one of A or B. So I have two items there, and I need to choose one of them. So multiply that times 2 choose 1. So now I have 3 spots remaining. I don't care what order of what those are in, whatever that is. This will still be the case. So what do I need to finish that out, multiplying that by? 3 factorial, right? So I have three things, and the order does matter, so I'm saying 3 factorial there. These will both give you the same number, which is, running out of space here, 0.3. Okay, everybody with me here? Okay, so we have P of 1, we have P of 2, we have 2 more to go here. We start moving a little more quickly. So P of 3 is just the probability that y equals 3. And so for y to be 3, I need to, again, I'm going to skip writing out so much here. I need the first element to be C, D, or E. And I need the second element to be one of those other that I didn't choose in the first one. And then the third position is the first time that I'm allowed to get a or a B. Well, let me write this out real quick. So I need a C, D, or E first, and I need a C, D, or E second. and I need A or B to come third. So I could write that out in a string of conditional probabilities, but I think you guys are getting the idea. So what's the probability that my first one is C, D, or E? Again, we saw that that was 3 out of 5. Assuming that my first one is C, D, or E, what's the probability that the next one is one of those other ones? 2 out of what did I hear? 4. Yeah. So I have 4 objects remaining, and I want to choose 2 of those things. So So say I chose C first, then I can choose from D or E second. And then for the third element there, I want it to be A or B. So I have 2 possible choices, and I just want one of those for the third spot. 1 out of 2 out of 3. Thank you. So I want to choose two of the possible 3 remaining things to be there. And so we could do this our counting argument way too. Again, 5 factorial total things. My first position, I want that to be a C, D, or E, so I have 3. I want to choose one of them. For the second, I have 2 remaining ones that I can choose one of them. For the third item, again, a 2, choose 1 there, and then finish it out with a 2 factorial. Whichever one of those is easier for you is fine. So this gives you 0.2. All right, and to finish this out, the probability of P of 4, which is the probability that y equals 4. Same kind of an idea. So for my first one, I need that to be C, D, or E, 3/5 probability of that. Second one, I need it to be one of those one of C, D, or E that I didn't choose. So I have 4 remaining. I can choose 4 of those. And my last one, I need it to be just one of the 3 that are remaining. So that's times 1 out of 3. So I need that third element to be whichever of C, D, or E that I didn't choose in the first 2 positions. And that will give us a 0.1. Okay, and again, the technical. Is everybody okay with that?
Can you write for the fourth one? What would it be?
Yeah. Okay, so for the first one, for the first element, I have 3 choices. I want to choose one of those. So out of 5 factorial. For the first choice, I want to choose one of them. For my second position, I want to choose one of the 2 of those things that is remaining. So 2, choose 1. For the third position, I'm going to choose the last one. So whatever C, D, or E I chose in the first 2 spots, I have 1 choice for that third element. So 1, choose 1. So again, the probability that y equals 4 means that the first time we see A or B is in the fourth spot. And then to finish that out, I have a 2 factorial there. Is that okay with everybody? So then, just as a technical condition, we can define this probability for any real number, is what I said. So the probability in general of, well, let's go with the little lowercase y. The probability of y is going to be equal to 0 if y is not equal to 1, 2, 3, or 4. So again, the probability of getting something other than 1, 2, 3, or 4 is going to be 0. So one of those other things has to happen. Yeah.
Going along with like how we do the 3 choose 1,
Mm-hmm.
or however for P4, would it be correct to say 3 choose 1, 2 choose 1, 1 choose 1, 2 choose 1, and then 1 factorial? Kind of like there's two
Yeah.
ways to choose. Okay.
That would work just fine, yeah. So the question was, when we get over to this position here, and this could have been the same for above too. So I've gotten to my 4th position, and I have 2 items remaining. I need to choose one of those. So this could also be written as 2 choose 1, and then my last element I just have 1, so that's kind of a trivial 1 factorial. That is equal to 2 factorial. So if you want to kind of step it the whole way through, go through each one of your positions, that works just fine too. Yes, sir?
And is that also the same way as saying 2 choose 2? 2 choose 2?
2 choose 2.
Back to the 4th and 5th elements, if you were choosing A and B.
So if you get down to the last element, is that the same as, so now I have 2 elements, I want to choose 2 of them. Not quite, because again, remember, a combination is an unordered thing. So if I have 2 elements and I want to choose 2 of them, that would mean like A, B is different than B, A. And here we're saying the order does matter. So so because I'm dividing by 5 factorial, I'm looking at all ordered lists of these things, A, B, C, D, E, A, B, C, D, and E. So the order does matter. So 2 choose 2 would shorten me by 1 possible outcome there. It's okay otherwise? Okay, so we have our PMF now, our probability of each one of these things. And we can now use that PMF to answer a question. So this is the tail end of that example. We want to use the PMF of Y to calculate the probability that it takes no more than 2 typings to identify an O-positive individual. So if you were given that question straight up without thinking about each option, that'd be pretty hard. But now that we've done all the work of figuring out the PMF, then this probability is pretty easy to calculate. So the probability that it takes no more than 2 typings to get someone with O positive blood. What possible values of Y is that going to involve? Yeah, right. So this is the probability that Y equals 1, or, so union, the event that Y equals 2. So I have probability of one event union with the probability of the other event. So you guys probably see where this is going, but are those 2 events disjoint? Can they both happen at the same time? No, I can't get my first O positive in position 1 and my first one in position 2. So those 2 things can't happen together. So this is just the probability of that Y equals 1 plus the probability that Y equals 2 because I have disjoint events. And again, so let's just, this is little p of 1 plus little p of 2, if you want to write it out that way, which is 0.4 plus 0.3 or 0.7. All right, so PMF, finding the PMF is the hard part here. Once we have that, questions like this are fairly straightforward. But again, you can see that our rules of probability that we looked at before do still apply. And however it makes sense for you to write this out is fine. Just kind of stepping through it very formally here. Everybody, we all okay here? Okay. So that's the probability mass function, just finding the probability of particular outcomes. Again, the other way that we can, sort of an equivalent way of telling the distribution of a random variable, is to look at its cumulative distribution function, or CDF. So for our random variable x that has PMF, little p of x, this is defined as, we're going to use capital F of x, and that's just the probability of being less than or equal to little x. And so here's maybe a nicer way of reading it. For any small lowercase x, the CDF of that number is the probability of being less than or equal to that number, or at most that number. So the probability of being at most x. And again, we find that just by summing up all the probabilities for all the numbers that are less than x, less than little x. So again, this means is all y such that y is less than or equal to x. So this is the CDF, the cumulative distribution function. Okay, so let's look at an example here before we finish up today. So here's our generic random variable. Takes on three possible values: -2, 0, and 3. And there we have the probability of each of those things. And we want to find the CDF of this random variable, and then also we can draw a graph of it. Okay, so remember, for each number x, capital F of x is just the probability of being less than or equal to that number. So we can set up our CDF is equal to some list of things here. So if x is less than -2, what is capital F of x? What's the probability of being less than -2? 0, right? I have no probability of being less than that. So my next range here is if x is bigger than or equal to -2, but less than 0. So what's the probability of being less than 0 here? 0.5. Right. So as we move from -2 to 0, our CDF is at a flat line of 0.5. If x is bigger than or equal to 0, but less than 3, then the probability of x being equal to 0 is 0.3. So we need to add that probably in there. So yeah.
Why would you go from -2 to 3?
So going from -2 to 3, the CDF will have two different numbers in that range. So I'll draw a picture in here which might make that a little bit more obvious. So this is going to be a step function, if that's kind of where we're going. So if x is between, let's say little x is 1, so the probability of being less than 1 is what? The probability of being less than or equal to 1, for example. So I have 0.3. I'll hit that kind of going backwards. I'll hit that at 0, but -2 is also less than 1. So I need to add in that probability as well. So this will be a 0.8. So if I'm thinking about this is the cumulative probability of being less than or equal to some number in between 0 and 3.
Why not 0.3?
So why not 0.3? It's because I want to include all the probability of being less than that number. So my probability of being less than or equal to 0. So for example, my probability that x is less than or equal to 0 is going to be,
What if it equals 0?
what if it equals 0?
Yeah. In the case of
So yes, the probability that x is less than or equal to 0 is 0.8. The probability that x equals 0, that's our PMF. So we're talking about a different thing here. Yeah, Mary.
So right there you have that x is greater than or equal to 0, but less than 3.
Mm-hmm.
So shouldn't it be 0.3 because the extra 0.5 is less than 0, which x can't be?
So again, so the question was, I have x is bigger than or equal to 0, so should it not just be 0.3? So let's say x equals 1, for example. So what's capital F of 1? Well, that equals the probability that x is less than or equal to 1. So the probability that x is less than 1, less than or equal to 1, includes those two numbers.
So what's up with the notation?
Yeah. So let me draw a picture here, and then I think that might make a little more sense. So just finish this off. If x is greater than or equal to 3, then we have the probability being less than that is 1. So let's draw a picture. If this is my CDF and this is possible values of x, we have 0, negative 2, let's start there, negative 2, 0, and 3. I'm going to, make this a little bigger. I'm going to draw the same picture if you already started writing. Okay, so again, I'm talking about the CDF is my cumulative probability of being less than that number. So if let me change colors. So if I'm at some value less than negative 2, we're saying the CDF is 0. So as we're moving along the real line here, we're at 0 until we get to 2, and there's an empty circle there, and we jump up to let's call this 0.5. So when I get to 2, I have positive probability there. So I go from, so if my CDF at 1.999 is still 0, sorry, at negative 2.0001 is still 0, but as soon as I hit negative 2, I jump up to 0.5. And then, so then, as I move on from there, if x is between negative 2 and 0, I'm not picking up any more probability. I still have the probability being less than or equal to that number is still 0.5 until I get over here to 0, and then I jump up a little higher to 0.8. So you see, this is very different than the PMF. The PMF lists just the probabilities for each value. The CDF lists sort of cumulative probability of being smaller than whatever that x value is on the x-axis there. And then from 0 to 3, we're flatlined again, but at 3 we jump up to 1, and this goes off in either direction. So I'm out of time, but yeah, question.
So then on that cumulative thing, let's say if we have a number like greater than or equal to 3, what's the probability that x is
Less than 3, and it has to be 1. Yeah, yeah. So I'll hit this again on Wednesday. We have a long weekend here. Have a great weekend, guys. We'll see you next week.